Hello, welcome. This time I'm going to talk about how to do a paired sample t-test in R. Think of a paired sample t-test as if you have repeated measures on a subject. For instance, you have a before and after. In, for instance, accounting, we might have before and after accounting change. Has there been a reaction? But what I'm doing here is I'm going to create a data frame with repeated measures. I have 300 subjects. It could be, for instance, companies. And then for year 2022, I'm going to draw then a sample from a normal distribution that has 4.5% mean and 8.5% standard deviation and populate the return on equity vector. Then I'm going to add another year, 2023, and I'm going to this return on assets add observations drawn from a normal distribution having 2% and having 20% standard deviation. So the second year ROA is going to be equal to the first year ROA plus the difference that's based on a 2% or a population mean and 20% standard deviation. Let's print some statistics for the data frame. So we have three variables. The ID measure, that's for instance company. And then we have the year 2022, 2023. And then we have ROA, the structure of the data frame. We can see it has 600 observations. 2 years, 2022, 300 observations, 2023, 300 observations. If I then want to do a paired sample t-test, I need to extract the before and the after. So that's what I'm doing here. I'm selecting ROA for 2022, put it into an object that I call ROA underscore 2022. I extract the ROA for 2023. And I put it into a vector called ROA underscore 2023. All I need to do now is to call on my t-test function where I provide my two vectors and then I tell it to be paired. We can see that the difference is not significant. We do know that the difference is drawn from a normal distribution having a population mean of 2%, which means that there should be a difference, but we can't detect the difference in it. Let's run this a number of times. So here the p-value is significant. It's at 0.1%, 0.2%. 2%, here it's 90%, so it's not significant. 3.2%, 4.4%, 0.5%, 4%, 0.4%, highly significant, not significant at all. Here you can see how, despite the fact that we know that there's a 2% difference in the difference, at least at the population level, the samples might not detect that. And that shows how weak the test is in the current situation. We fail to reject the false null hypothesis in many of the samples. So how can we then become more confident that we can reject a false null hypothesis? Well, the answer is rather easy. We increase sample sizes. 300 observations, maybe we can expand it to be 500 observations. We still have some situations where we don't have that. We then expand it even 1000 observations. Now you can see hardly any p-value indicates non-significance. So we can reject the false null hypothesis. So that's also illustrating the power of power, the importance of sample sizes. It's difficult to do a lot of studies on very small samples. We need to expand it. The greater the variability is in the underlying data, as I'm inserted in here, the greater the slump needle, a larger sample is. So that was a sort of a side question. I've illustrated how to run a paired sample t-tests in R using random data. Thank you very much.